In today's episode, we dive into two fresh ideas reshaping how we understand large language models. One from MBZUAI's VILA lab, where LLMSurgeon tries to infer a model's hidden pre-training mix just from its text, and another from ByteDance Seed, University of Virginia, and UC Berkeley, which treats LLMs like noisy Shannon channels to explain scaling laws. From auditing data mixtures in LLaMA and OLMo to predicting when more compute backfires, these papers reveal the surprising mechanics behind modern AI. Let's explore the first paper, LLMSurgeon Diagnosing Data Mixture of Large Language Models. LLMSurgeon from MBZUAI's VILA lab tackles a new auditing problem the authors call data mixture surgery, inferring the domain-level pre-training mixture of a large language model from generated text alone without access to weights or training data. The method assumes label shift and uses a three-stage inverse correction pipeline. Train a proxy domain classifier on reference data, estimate its soft confusion matrix C to capture systematic domain confusions, sample the target model with neutral prompts, then solve a constrained linear inverse problem to recover the latent mixture prior pi from the observed classifier outputs. To benchmark this, the paper introduces LLMScan, a verifiable suite built from open source models with known data recipes, including LLMA1, OLMo, Amber, Pythia, GPT-Neo, and StarCoder, spanning 6 coarse domains, 17 mid-grained pile domains, and 87 programming languages. On LLMScan, LLMSurgeon reaches 95.14% overlap accuracy on LLMA1, 7B, and 94.46% on OLMo1B, while the strongest aggregation style baselines stay near 50%. Even on fine-grained StarCoder, it still improves over the best baseline, 30.37% versus 27.54%. Ablations show that fine-tuned Distilbert gives the best proxy classifier and that merging semantically indistinguishable sources like C4 and Common Crawl is essential to avoid ill-conditioned inversion. The authors also show the method can track training dynamics across checkpoints and estimate injected toxic data proportions with 97% to 98% accuracy in a GPT-2 sandbox, positioning LLMSurgeon as a practical post-hoc tool for transparency, bias analysis, and safety triage of foundation models. Let's explore the second paper, LLMs as Noisy Channels, a Shannon Perspective on Model Capacity and Scaling Laws. ByteDance Seed researchers from the University of Virginia and UC Berkeley recast large language models as noisy communication channels and derived the Shannon scaling law from the Shannon-Hartley theorem, mapping model size n to channel bandwidth, training tokens d to signal power, and perturbation-dependent noise to a denominator that includes both data noise dd, delta, and model interaction noise c, d, n, gamma. The paper explains why standard monotonic power laws from OpenAI and Chinchilla break under catastrophic overtraining and quantization-induced degradation, where performance becomes U-shaped instead of steadily improving. On Pythia and OLMo, evaluated on YK text DO, Gaussian weight noise at current decibel to dis decibel, SFT on GSM WITK, Social IQA and StarCoder Python, and GPTQ quantization at cat bit, 3-bit, and 2-bit, the full law consistently achieves the best fit, with average R2 above 0.95 inches, most settings, and 0.9555 on Pythia at 10 decibels versus 0.8251 for the strongest baseline. A simplified 6-parameter variant still reaches pooled R2 equals 0.945 on long horizon token extrapolation, while the full 9-parameter form is strongest for joint extrapolation, predicting an unseen 12B Pythia model up to 307 B tokens at pooled R2 equals 0.847, where OpenAI and Chinchilla drop below 0. The central result is that scaling only helps when signal-to-noise ratio stays above a capacity threshold. Otherwise, more parameters or more tokens can amplify noise and worsen loss. That's a wrap on today's AI paper highlights. Thanks for watching.